Hello. So our next challenging problem is a chain of length L is placed on a smooth spherical surface of radius r with one of its end fixed at the top of the sphere. What will be the acceleration of each element of the chain when its upper end is released? Okay. So you are given that there is a chain and which is the chain is placed on a spherical surface which is fixed. You are supposed to calculate acceleration when the chain is released. Let me draw the chain here. The chain is having a length L which is less than the length of quarter circle. L is less than pi r divided by 2. Okay, the chain was fixed here but it was suddenly released, and when it was released it starts moving along the surface. This angle is theta naught, and theta naught is equal to L divided by r, where r is the radius of a spherical surface. Okay, let me consider very small element of angular width d theta. This small angle is d theta at an angle theta. Okay, so this is a very small element which I am going to highlight here. This is a small element is having a tension T here and T plus dt along the tangential direction on the other side. With that, there is a force, gravitational force in the downward direction dm into g. One component of this force dmg will be along the tangential direction, and the acceleration of the elementary part is also along tangential direction. So if I apply Newton's law along tangential direction, I can write t plus dt minus t plus dm g sine theta. Why dm g sine theta? Because this angle is theta and this angle is also theta. So the component of this dmg along tangential direction will be dmg sine theta, and this should be equal to dm into a. Okay, we are going to integrate it both sides from 0 to theta naught, from 0 to theta naught, and from 0 to theta naught. T and T gets cancelled and we'll get dt here. As you can see that the tension on both the ends of the chain is 0. At this end it is 0 because nothing is pulling it in this direction, and for this end also tension is 0 because there is no mass beyond this particular point. So the limit of the tension at theta equal to 0, tension will be 0, and at theta equal to theta naught also tension is equal to 0. So this first integration becomes 0. For the second integration, I am going to write dm. dm is equal to m upon L into r d theta. So we just write down the value of dm, m upon L into r into d theta. D theta will go inside, and when I'll integrate it, I'll get 1 minus cos theta naught. Integration of sine theta is minus cos theta, so I'll get 1 minus cos theta naught. Okay, and on the other side I'll get m into a, because when I'll integrate, a will come out, so it will be integration of dm from 0 to theta naught. You have two choices. You can write down the value of dm here, then you integrate it from 0 to theta naught, or you just take out the term acceleration out and then integrate dm. When you'll integrate dm, you will get total mass m. Okay, m and m gets cancelled and this is your fantastic answer. Acceleration is equal to g divided by l into r 1 minus cos theta naught. Theta naught is l divided by r. So this is the acceleration of the instantaneous acceleration of the chain. Okay, so now I am giving you my next challenging problem. The next challenging problem is again a fantastic problem from electrostatics, and you are given a chocolate figure of Santa Claus wrapped in aluminum foil and electrically charged and hangs on insulating cord. The figure slowly loses its charge because of air, has a small but non-conducting conductivity sigma. Assuming that the air conductivity is everywhere the same, how long will it take for Santa's charge to halve? So you have to find out a relation between rate of loss of charge and the instantaneous charge. Okay, so you have to try it and write down the answer in comment box. This time I am giving you three challenging problems. The next challenging problem is from magnetic field. You have a charged particle which enters in a region in which there is a frictional force proportional to the particle's speed. This is a different type of question because usually we don't have friction force in magnetic field. So here you have to apply uh, magnetic force as well as friction force. So in first case there was only friction force which was there to stop it. In second case there is friction force as well as magnetic force. So the distance told was 6 centimeter in the second case. In third case you have doubled the magnetic field and you have to calculate the distance traveled by the charged particle in that case. These are the tentative paths. When the magnetic field is absent, the path is a straight line. When the magnetic field is present, it is a sort of a spiral. When the magnetic field is double, the spiral is further tilted because the magnetic force is higher, so it will turn the charged particle more. Okay, giving you one more challenging problem, especially for class 11 syllabus. There is a funnel in which is placed upside down on a table as shown in the figure, and 1000 centimeter cube of water is poured into. The area covered by the funnel on the table is 200 centimeter square and the height of the water is 18 centimeter. What is the minimum mass of funnel if it is not to be lifted away from the supporting surface? So this is again a very fantastic problem of fluid where you have to apply your mind, and there are 2 3 ways of solving this problem, but if it clicks, the problem will take hardly 30 seconds. So you try it, and we'll discuss the solutions of these three problems in next 2 3 videos. You try these problems, share with your friends, discuss with your friends, and write down the answer in comment box. Also try to give these ideas to your friends so that they can also get benefit of it. So stay tuned. Thank you very much and enjoy.